This YouTube video explaining ternary diagrams is produced for geohubliverpool.org.uk. In this bowl there are wooden beads painted red, blue and green. Because there are only 3 colours, this makes up a ternary system. Any set that only has 3 components can be called ternary. You can see that there are different numbers of each colour. It's difficult to see how many beads there are of each colour. Here we have separated the beads so you can see how many there are of each colour. You will notice that the numbers are chosen deliberately to make the mathematics easy. Another way to look at this data is as a fraction. Note that the total of all the beads is 1. To turn the fractions into percentages, we multiply by 100. This leads us to the figures 10% red, 30% blue, 60% green and 100% total. The total is always 100% for ternary systems. We must remember these numbers. This triangular diagram is called a ternary diagram. You can see that we have labelled the corners with the colours of the beads. We have also coloured the lines on the graph and labelled these axes in colour to match. If we start with the red corner, there are parallel red lines that start at 100% and then drop in 10% intervals to finish at 0%. The red beads are counted for 10% of the total, so we need to find the red 10% line. Anywhere along this line is 10% red. The figure for the blue beads was 30%, so we have to move along the red 10% line until it crosses the blue 30% one. We will mark this point with an asterisk. It fixes where the whole collection of beads is located on the diagram. What about the green beads? If we look at the crossing point, there is also a green line and its label says 60%. Remember that the values on the 3 axes always have to sum to 100%. This second bead set has numbers that make the mathematics more tricky. We get the fractions by dividing by 42, the total number of beads. The total fraction is 1, since this is a whole collection. When we start to convert the fraction to a decimal, it gets more difficult. You can see on the calculator that there are lots of numbers after the decimal point. We're going to limit what we record to 3 decimal places. When we do this, we round up the last figure to a 7. Again, for the blue beads, the calculator shows that it is not an exact decimal, so we will just show 3 decimal places. We have the same problem with the last fraction, so we record 0.357. Adding the 3 decimals together gives exactly 1. This will not always be true because the 3 decimals are not exact values, and we were just lucky that this worked. You might need to adjust the last figures to get exactly 1.000. When we plot onto the ternary diagram, you will see that the last figure is not very important. You'll remember that we get to the percentages by multiplying each decimal by 100. The percentages always sum to 100. To plot these percentages onto the diagram, start with the red data. We are using a ruler to find where the 16.7% red line goes. Place the ruler at the appropriate point on the red scale, between 16 and 17 and nearer to 17. The exact point is really a guess. The ruler has to stay parallel to the red lines, and you can use the blue scale to help you. Mark this line with your pencil. Next, we find the blue line using the ruler in the same manner. Mark this line with a pencil. You now have two intersecting lines. Where they cross is the correct location for this set of beads on the ternary diagram. Again, we will mark it with an asterisk. We will finish this video with 3 practical examples of using ternary diagrams. Sandstones are made from 3 main components: quartz, feldspar and lithic fragments, or fragments from older rocks. The red sandstone here has 96% quartz and 4% feldspar grains. That puts it right at the top of the ternary diagram, so we call it a quartz arenite. This sample has a high quartz content but also 10% feldspar, so it is to the left of the centre line in the diagram but still high up. We classify it as a subarcose arenite. Soils are made up from clay, sand and silt. These 3 components are plotted on the vertices of the triangle. The area inside the diagram is divided to give named types of soil. This diagram is only for the UK. Other countries divide the diagram differently while still using clay, sand and silt as the basic units. 60% of the Earth's crust is composed of feldspars. The differences between the feldspars happen because of the amounts of potassium, sodium and calcium ions they contain. This image of granite shows 4 minerals. The large pink crystal of orthoclase feldspar and the smaller white crystals of plagioclase feldspar are marked by red arrows. The other 2 are tiny black mica crystals and grey quartz crystals. We can see on the left of the diagram the alkali feldspars from potassium aluminium silicate of orthoclase and microcline at the top left, the same chemical composition but with different structures, down to albite, that is sodium aluminium silicate, at the bottom left. Between these are crystals with mixtures of potassium and sodium. Across the base of the diagram are the plagioclase feldspars from albite, sodium aluminium silicate on the left, to anorthite, calcium aluminium silicate on the right, with mixes of sodium and calcium feldspars between. You will notice that the other side of the triangle is empty. This is because potassium aluminium silicate and calcium aluminium silicate are immiscible. They will not mix together in the same crystal. This is clearly shown by how much of the ternary diagram is empty.